Saxon Advanced Mathematics. Welcome, my students, to lesson 47. In just a minute, we're going to talk about vertical sinusoid translations. I know that sounds really fun, but you're going to love it. But first, I want to talk about this unit circle. This is a picture of a completed unit circle, and I posted last week. Trying to think if my YouTube students would have found it. Well, in any case, I'll show you again. I have a video, it's about, I think it's 39 minutes long, and it explains how to fill this out. What this unit circle shows you is in green. It shows you all of our quadrantal values. In red, it shows you the value of cosine and sine in that order, cosine and sine, for all four quadrants of a 45, 45, 90 triangle. That's the red. The orange shows the 30 degrees of a 30, 60, 90 triangle. There it is in this quadrant, there it is in this quadrant, and in here, and in here. All the oranges are 30 degrees plus or minus from the x-axis, and then the blue are 60-degree angles. Each cosine and sine is given to you. Oh, no, the cosine and sine are all written out here so that you have the values of those two trig functions for every single degree measurement. And then we also show the size of the angles as measured in radians, so that if we're given a problem in radians, we don't even have to convert it. We can just find the numbers on here and go directly to the values for sine and cosine. This is going to save us so much time and trouble in doing our homework. And we're not going to use it in lesson 47, but I think in 48 we will. But from now on, my rule is this. If you can take a blank one of these forms and fill it out, then you can use the unit circle to help you calculate your problems. You don't have to show that work in the problem. So what you're going to want to do is memorize how to do this. And again, like I just said, there's no new information on here. It's all just a collection of things we've already studied, and that unit circle video that I will link to the bottom, the description of this lesson. And I'll link to you the PDF, the blank form that you fill in. If you can fill it out, you can do it. For local students on the test, I'm going to give you a blank one of these forms and expect you to fill it out correctly, and then you can use it on the test to help work your problems, all right? So we're going to rely on this unit circle like crazy from here on out. It's a super useful tool, and you'll be able to take it forward with you to pre-cal and calculus classes if that's where your path leads you. And if you've got this all memorized, I'm sure your professors will be very impressed. All right, so make sure you have watched this video and you know how to complete this. You've done at least one. And then as part of studying for the test, which is coming up next week, make sure that you know how to fill it in. Again, I'll say it for the third time. There's no new information on here. It's just a better way of organizing a bunch of things we've already learned. Okay, there's my plug for good old unit circle. Let's talk about vertical sinusoid translations. First, let's just talk about this word sinusoid again and what it means. A sinusoid is a pattern where something goes up and down in a regular, peaceful rhythm. Now, it can be a sine curve or it can be a cosine curve. Those are different types. But sinusoid refers to this general pattern or rhythm. And here is an exciting true life story from my life. This past week, my husband was in the hospital. He's fine now, don't worry. He did not have like a heart attack or anything like that. He didn't have any pain. He didn't have any vent, but he did have some problems with his heart because what happened is that it was arrhythmic. It wasn't making this nice little sinusoid pattern. It was beating too fast, and so it was choppy and irregular. And so he went to the emergency room. I got to go to the emergency room too. It was exciting. And they put him on medications to slow his heart. And the whole goal was to get him back to a sinusoid rhythm. And when I heard the doctor say that, I just wanted to hug him because I had just taught the lesson. And he's like, yeah, we just want to get him back to a nice sinusoid rhythm. I'm like, dude, you make me so happy. You make math so relevant to like normal everyday lives. So our hearts beat in a nice sinusoid rhythm. And if we get thrown off that pattern, then the doctors know something's wrong and they get us back. All right, so sine and cosine are two sinusoid functions. We call it a periodic function. And the periodic, that word, I mean, function, we know what that is, and we can see right away it passes that vertical line test, doesn't it? A function is a matching of inputs and outputs. And we'll get into that, but I don't want to talk too much about function now. Function is just a word that describes lots of things we do in math. It's not as fancy or fussy as we think. Periodic is the important thing. What I want you to remember is that we can measure the functions by looking at the same point. Like here, I'm looking at the top of the curve. So each down and then back up is one period. You can measure it from any place you want, but we usually measure either from the top or the bottom. All right, now let's just remember what our basic periodic functions look like. For sine, we remember that we're measuring these in, usually the basic ones we're measuring in 90-degree increments. Sine, this is the y-axis. This is either the x or the theta axis. We can call it either one. Sine starts in the middle. It comes up, and then it goes down, and then it comes back, right? This is the low point. All right, this is what we call a positive sine function. We can also have a negative sine function, and I want to toss that into the mix right now, just so you'll remember. Again, we usually draw that little arrow. I'm not sure why, but that's the way periodic functions are typically notated, is with that. Here, this is a negative sine function that I'm going to draw for you now. Here we still start at the middle, but we go down, then up. Here we go up and then down, right? So it's reversed. So that is what a negative sine function looks like. We covered this in the previous lesson. I'm just recapping because we're going to build on this. So I want it to be clear in your noggin. All right, that's the way sine curves look, positive and negative, or sine, yeah, I call them curves. Let's look at cosine over here. So this will be our positive cosine function. Again, we have the 90 degrees. And again, this keeps repeating, and it repeats in the negative direction too, doesn't it? I'm just keeping my pictures simple. I'm showing you one period of each of these. All right, now on the cosine side, it looks a little different. Because on the cosine side, we start at the top of the curve. And then we go down, and we come up. This is, again, this is x, this is y. This is what we would call a positive cosine curve. And then the negative is going to start at the bottom. Here's my 4 quadrants at the bottom and up and down. So it's going to go like this. That's a negative cosine curve, all right? So that is a recap of what we've done. We also said I don't want to say that right now. Never mind. I'll add that later. Okay, so what we're going to do in this lesson is we're going to talk about translating this vertically. Okay, let me just say another thing. This we call the center line, and the distance from the center line either up to the top point on the curve or down to the bottom point of the curve, we call the amplitude, right? So this is the center line. And what we're talking about in this lesson is what if you want to shift that up? You want to do a vertical translation. So you want it to go up or down the y-axis. How would you make that change? Let's look, and I'll explain it in a problem. In this type of problem, John draws pictures for us and then asks us to write the equation. He says, write the equation of the two sinusoids shown here. Sinusoid is the general term. It doesn't mean a sine curve. It just means that shape. All right, and this is what he draws for us. I'll make it kind of big so that you can easily see it and we can talk about it. When you're doing these problems, you don't have to draw the picture. You can just look at it in the book. In this problem, we're given three numbers here on the y-axis. The 4 is written here, and then the 6 and the 2. That gives us a lot of information about what we want to know. But we also want to know about this. I'll give you a second to, oh, this, yeah, that's the right place, okay? And then what John wants us to do is he wants us to write the equation of this sinusoid. Okay, so the first thing that we have to do is decide, is it positive sine, positive cosine, or negative cosine? And that's why I drew those pictures for you just a minute ago, so you'd have that all fresh in your brain. When it comes out of 0, we know that it is a positive, and it goes up. When it comes out of 0, we know it's sine. When it goes up, we know it's positive sine. So we know that this is a positive sine curve. So we can write y equals, and I'm going to leave some space here, but I'm going to write sine of theta. We know that it's that. Now, we're going to add some numbers to this, though, to show that we've adjusted it. This first number is the center line. And we add that to our equation at the beginning. Then, we're going to put in this place the amplitude. 4 and 6, the difference is 2. And then we can double check it. 4 and 2, the difference is 2. So we know that our amplitude is 2. And I'm just going to write that right here. So that's as easy it is to write the equation of the sinusoids based on what we've tackled so far. Center line goes first, plus this, and then the sine of theta. I'll show you, I think we have a negative one coming up, so you'll see how that looks. Yes. Okay, so this is the answer to the first problem. Now let's, this is like an A and a B. There's 2 parts to the first one. Now, and I would also say that in the book, this keeps going and then they have it go backwards too. We're focusing in on the part we really need. Here comes the next one, ready? And this time we're learning about center and amplitude in this lesson. So that's here. Because what we've done is we've shifted it up by moving the center line from 0 up to 4. But what's fun about these is you don't have to draw the picture or do anything different. You just read the gauge over here. You just read the scale of the numbers. And that's the only way we need to worry about it. All right, here we've got -10, -6, and down here, -14. And then we have our 4 points. And this time, we see that it starts in the middle, but it goes down. Oh, okay. So we see, okay, it's a sine curve because it starts in the middle, but it's a negative sign because it goes down first. So we're going to write y equals, and then we'll leave space. But we know that this in between is going to be a negative. And again, this is, put those in so we're clear. All right, so this is where we adjust for the fact that it's a negative sine curve. Okay, now we're ready to put in the center line and amplitude just like we did before. The center line goes here, so there's a -10. Now we calculate our amplitude. It's the difference from the middle to the extreme, and we see it's 4 units here, 4 units there, so this is a 4. All right. The center line and the amplitude are exactly the same as last time. What we see this time is that when you have a negative curve, the minus sign goes here. This minus sign relates to this minus here. This has nothing to do with the shape of the curve. This minus sign tells us that we have translated down 10 units. All right, let me just add this. This is the center line. And this one is the amplitude. Amplitude can never be plus or minus. Amplitude is like absolute value in that it's just the distance between those 2 points. So it's never going to be negative. Even though these are negative numbers, it's still 4 units in between. So that's why we put the minus sign for the curve in this place. This will always be positive. This place, it can be positive or negative. So we don't want the sign of the curve reflected out here. That goes in the middle. Okay, more. Sine curves will blow your mind a little bit in the beginning, but once you get the hang of them, most students find them fun. I did have one student last year. I mean, we were in the grips of COVID and life was crazy, but she got off on the wrong start with sinusoids, and you know, they just drove her nuts for months until we finally sat down and just started from the beginning and hashed it all the way through. So that's a really good lesson for all of us, that sometimes if we're just not in the right place when we get introduced to a topic, we'll never learn it right. So if you ever find, man, I am just stuck on that certain kind of problem, they drive me crazy, just let me know and we'll just go from A to Z and recap the whole thing and see if we can't jumpstart your brain. Okay, B is another two-parter, and again, John's giving us the curves and asking us to write the equations. So it's like last time. I want to bet you $5 that we're going to look at cosine this time, though. I don't know, we'll see. Okay, here's the first picture. I'm going to draw them side by side this time. -8, -5, -11. Hard to read. John tries to like put a little gap in his line there so you can read the value of the center line. I tend to write it over the top. It's kind of hard to see. And then we have the 4 quadrants. I like to put out the dots so that I can see where the curve is going to go. Pretend it's perfect. And we look at that and go, okay, is it a sine or a cosine? Is it positive or negative? All right, this looks like a cute little cosine curve, doesn't it? And let's see, we have plus theta going this way, and we have y up here. So y equals, and then I leave my space, and I write cosine of theta. And I know because this is a positive curve, there's going to be a plus there. The first number is the center line. The second number is the amplitude. The difference between -5 and -8 is 3, and then I double check it by looking down. Yep, it's 3. So there is the answer to the first one. Again, center line, amplitude, sine of the function. And then here comes the other one. Again, you don't have to copy I'm just doing it so that we can look at the numbers and talk about it, and you can see it better. Okay. And once again, we think about those 4 functions that we drew pictures of back here in the beginning, right? That's why I gave you those, because they'd be fresh in your mind. This is this one, isn't it? It starts at the bottom extreme and then it goes up. So this is y equals, leave space, cosine of theta, and this is going to be the negative in the middle. Center line is 7, so that goes here. Amplitude, 2 up, 2 down. And this is the correct answer for this one. Okay, so that's what we mean by vertical translations. We're moving that center line down to -8 or up to +7. It doesn't matter. It doesn't change the picture. We don't really have to change the way we graph it. We just make those adjustments by the numbers here, and that makes it super easy for us just to go, okay, center line and then amplitude. We learned how to deal with changes in the amplitude before, and so that's not new. What's new is just the center line and the positive and negative. Okay, that is the first part of this lesson. Ready for the second? All right, the topic is arctangent. All right. I want to do a debrief on some of the words we've been throwing around with trig. They don't necessarily specifically relate to this, but I want to make sure this is all clear in your head. Let me flip to a fresh page so that I can get this all done. We're going to kind of do a review just like we did of the other stuff. Let's talk about reciprocal trig functions. Their names are cosecant, secant, and cotangent. We can write them as they relate to the parent functions, right? They're 1 over. Or we can write them as a pair of sides, right? Hypotenuse over Oscar, hypotenuse over Arthur, or Arthur over Oscar. And we say them as cosecant, secant, and cotangent. Okay, those are reciprocal trig functions. We take the very same pairs and we just flip them and give them new names. All right, that we've dealt with. That's one thing. The other thing that we want to talk about more today is what we call inverse trig functions. Everybody gets confused about the difference between reciprocal and inverse. That's why I'm going through this. Okay, this has to do with, primarily it has to do with, well, the way we've learned it so far is in dealing with the buttons on the calculator. We have a button that says sine, a button that says cosine, a button that says tangent. These are what we call the parent functions. They're on the front face of the calculator, right? We don't need to use the second key. They're when we know the degrees of the angle and we want the decimal. And remember, by decimal, we mean the ratio of the sides, right? This would give us a decimal number because we'd have number over number and we could simplify it to a decimal. That's what we use these buttons for, is for the parent functions. Now we have another set of buttons on the calculator. And we have used them. You usually have to use the second key to access them. Okay. All right, they're hidden. And these are what we call the inverse functions. The inverse functions have nothing to do with reciprocals, but here's why it's insanely confusing. See that -1? Doesn't that make you think of flipping it down to the bottom, which is how we create reciprocals? This little notation adds so much confusion to the water. Don't worry about that. These buttons are useful when we know the decimal or the fraction, right? We know these numbers and we want the degrees. We want to know how big the angle is. Okay? So inverse functions are when we know the sides or the decimal, the fraction or the decimal, and we're trying to find out how big is the angle. And that's where we run into this problem that for any given decimal, it might lead us to an angle like that, let's say, right? But let's say it's a 30-degree angle that our answer is, but because we have this problem of spinning, it's a 30-degree angle, it's also a 390-degree angle, it's also a what, 450? We keep getting multiple spins. Multiple spins lead to many angles. So we need to find a way to lock that down. We cannot have all of these different angles, right? And we call the first one 30 degrees. We'd call it the terminal angle. And then all those other angles where we're adding 360 over and over, they would be like 390, 750, and so on. We call those coterminal, meaning they have extra spins built into them. When we talk about inverse trig functions, we need a way to factor out all of those extra angles that we don't want. We just want the terminal angle. We don't want all the coterminals, right? And that's why we use the uppercase in the arctangent. Okay? When we say arcsine, arccosine, or arctangent, any one of the functions, this uppercase A tells us, that is notation that tells us terminal angles only. We don't want extra spins. Okay, so what we're doing is we're putting a limit on where we want our answers to fall. Let me write it and see if that makes sense. I promise I'm getting somewhere. I just don't want to lose you along the way. Once we get into this, you'll see it actually kind of makes sense. And I think we're just doing one problem because we've already done this for arc sine and arc cosine. But now we're talking about arc tangent. Okay, here's what I want to talk to you about. I want to explain what this means. To prevent an infinite number of coterminal angles, to prevent that spinning issue, we limit solutions to 2 quadrants per function. 1 positive, 1 negative. Now let me draw you an old friend. You know this guy, right? This is our list that shows the value, positive or negative, of the trig functions in the various quadrants. So remember, this is first quadrant, this is second, this is third, and this is fourth. We don't talk about those by name a lot, but they do have names, and they're typically Roman numerals, and it's 1, 2, 3, 4. So mathematicians got together and said, look, we don't want all these coterminal angles popping up. When we're working with inverse trig functions, we want to keep it simple. So we're going to choose 1 positive quadrant and 1 negative quadrant for each function. And we're going to say we only want the answers that fall into those 2 quadrants. That's how we're going to keep all this stupid extra spinning out. So here's what we've agreed upon. For sine, the 2 quadrants we'll use are 1 and 4. All right? 1 and 4. We get a positive and a negative. Beautiful. Let's go to tangent. For tangent, we're going to do the very same thing. It's positive and negative in the first and fourth. So we're going to keep those 2 the same. Okay? Those are the only 2 quadrants where we're going to find our answers when we're working with inverse functions. But when we go to cosine, you'd like to say, oh yeah, let's just use first and fourth, right? That's not going to work because cosine is positive in first and fourth. So that means we're not going to get our full set of solution because we have to have 1 positive and 1 negative. So this is how we've come up with an answer. For cosine, we're going to use the first quadrant and the second quadrant. All right? So cosine is a little freak child. He has to go this way to get his second quadrant, whereas sine and tangent go this way. That's how my brain sees it. Now, the way that we write these rules when we practice them, it's the same information, but we're going to write this in a slightly different format. For sine, we're going to say that we want to find values for sine, angles for sine, that are between negative 90 and positive 90 degrees, right? Because if you think about this, this is 0 degrees, and this is 90, right? We know this. This is 180. This is 270 down here, right? So instead of saying first and fourth quadrant, we say between positive 90, and look, you could think of this as negative 90, couldn't you? That would also work. That's how we write the acceptable range of answers of terminal angles for the sine function. Tangent is the very same guy, right? That is, we'll take angles between minus 90 and plus 90, right? First and fourth quadrant. It's another way of saying the very same thing. Cosine is the one where, again, he's being a little difficult. We say we'll take them between 0 degrees and 180. All right? So if this makes sense to you, this is just another way of saying the very same thing, right? We're just writing it by referring to the degrees rather than the names of the quadrants. But it's the very same quadrants as we said here, and cosine is different for the same reason it was different here. It's because cosine is positive in both of these, so we have to go this way to get a positive and negative. This we're going to start seeing in a lot of our problems. Because when we work with inverse trig functions, We always want to put the limits on it, and you'll start seeing these in the problems. And, okay, so hold on to that. Almost ready to do this. I know, this has been a long preamble, right? This is our only remaining example, 47.3. John tells us to evaluate, and then he says, find the arctangent of the tangent of 135 degrees. This A tells us put the limit on it. Okay, so we remember what is the limit. That says that our solution has to lie between positive 90 and negative 90 degrees. All right, that is implicit as soon as we see that A. That is the way we limit our trig functions. Okay, so let's figure out what the heck is going on here, because right now my head is just swimming, right, with all this stuff we've talked about. Let's draw a picture and see what we can figure out. Let's start with the tangent of 135. We could use our unit circles, but for right now, I want to stick with our old school drawings. Okay, 135, we know that's 90 plus 45, so that's right down the middle of the second quadrant. We know this is a 45 degree angle, sorry. We know that this is 1 and 1 and square root of 2. We're supposed to find the tangent. We know that tangent is over Arthur, right? We're starting with this. We start in the parentheses. Later we'll come out here and do this, all right? We know that the tangent of this, okay, equals, the opposite is 1. The adjacent is 1. We know that tangent in the second quadrant, let's see, it's plus, minus, 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 plus. I'm just doing this quickie chart. Again, this is all on our unit circle, but I want to start using the unit circle with a problem that's a little more familiar. So we're doing it old school here. Tangent in the second quarter is negative. So this is negative 1. We can simplify this to negative 1 like that, right? So that means the tangent of 135 degrees equals negative 1. We're going to put that in like so. So just like any other kind of problem, we work within the parentheses, right? We do the work in the parentheses first. Okay, now we know that we're limiting this to angles between positive 90 and negative 90, first and fourth quadrant. And now we know that this is the decimal number. Okay, this isn't the size of the angle. This is when we know the decimal, but we don't know the degree of the angle. But, so we have to think a little bit about what ratios would give us that. And another way to look at this is to remember that with a 45-45 angle, tangent is always a whole number. It's always 1 because these two sides are the same, right? So what we can do is go, okay, well, let's draw a picture of the fourth quadrant angle because this is negative, and we know that tangent is going to be negative in that fourth quarter, right? It's positive in the first quarter. So since we have a negative value here, we know, okay, we're interested in the fourth quarter. Let's just look and see what happens with a 45 degree angle. 1, 1, square root of 2. We know that it would be negative down here. Tangent of a minus 45 degree angle would be equal to 1 over, this would be a negative 1, right? Or you can look at it this way, it's a negative right? So this tells us that this negative 45 degree angle will give us the decimal number that we're looking for. Remember that with inverse functions, we know the decimal or the ratio. We're looking for the degrees. So just by playing with these triangles, we can see, oh look, this number must come from these two sides. We know it has to be in this quadrant, right? If it was a 60 or a 90, it would have, you know, square roots and weird numbers in it. So the fact that it's just -1 tells us it must be this triangle in the fourth quadrant, and that's a -45 degree angle. So the answer to our question is that the arctangent of -1 equals -45 degrees. We knew the decimal or the fraction. We were looking for the degrees. We were limiting it to those two quadrants. So even though we got the same ratio of sides here, this was in the second quadrant, so that couldn't be the right triangle. We had to take it to the fourth quadrant because that's the only place where our answers are allowed to fall. That's crazy, isn't it? It's kind of confusing. It's kind of complicated. It will get easier as we go. Just remember that inverse functions, this is what I want you to remember most and best of all. Inverse functions are when we know the decimal or the fraction, either way you can look at it, and we want the degrees. And that's exactly what we did in this problem. We knew that the fraction or the decimal had to simplify to -1, and we knew this triangle would be the one that would get us that, right? 1 is equal to 1/1. And then we used that to figure out what size angle it would be, and we wrote it as a negative angle, all right? And we knew it had to be in the fourth quadrant. That was a hard problem. Guess what? We're done. Goodbye.